Okay, right, just a reminder, we're scheduled for our first exam this Friday, and there are sample tests on the course website. You certainly want to try these before Friday. Okay. Your first assignment, you should get that back graded together with a solution set on Wednesday, so you'll be able to go over it before the exam. All right, do you have any questions? All right, today we're going to extend the binomial heap to the Fibonacci heap data structure. And today we'll only take a look at how you do this extension. We won't actually analyze the complexity of, or the amortized complexity of Fibonacci heap operations. What we'll see is that the Fibonacci heap supports two operations in addition to those supported by the binomial heap. The two being the remove, which is an arbitrary remove. So external to the data structure, the user has pointers to nodes in your Fibonacci heap and says remove the item that's sitting in this particular node. Okay, so you get an arbitrary remove. And you have a decrease key. Again, for the decrease key, the assumption is that the user is keeping pointers to nodes in your structure and comes to you and says decrease the key of the item sitting in this particular node. Okay. All right, so we're going to support these two operations in addition to the three supported by a binomial heap. The actual complexity of the operations, the actual complexity of binomial heap operations remains the same here as it was when we looked at binomial heaps. The remove operation and the decrease key have a rather poor actual complexity order of n. Okay. So if you simply look at the actual complexities, your conclusion would be that this is a pretty lousy data structure. Okay. However, the amortized complexity is fairly good. In particular, the amortized complexity of the decrease key operation is order 1, which is very, very good, and which makes this data structure very useful in the implementation of greedy algorithms to arrive at provably good, from the asymptotic complexity point of view, greedy algorithms. Okay. Now, today we'll take a look at couple of applications of the Fibonacci heap and then how you perform the various operations in the Fibonacci heap. We won't actually do the amortized complexity analysis. I'm going to let you read the amortized complexity analysis from the text. Alternatively, to the website, I've added a pointer to a lecture that I gave in the past, which is very similar to our last lecture, and it kind of goes through the analysis of the Fibonacci heap. So if you follow that link, you can watch an old lecture on Fibonacci heap analysis and see why the amortized complexity is what I've claimed it is. Okay. All right. So let's take a look at a couple of applications. So two greedy algorithms we're going to see, and actually when I say see, I just mean I'm going to try and refresh your memory about the two greedy algorithms. The first is Dijkstra's shortest path algorithm. It finds the shortest paths in a directed graph from a given source vertex to all destination vertices in the graph. Okay. So I have a directed graph here. It has a total of 7 vertices. The given source vertex is 1, and you want to find the shortest path from vertex 1 to the remaining 6 vertices, 2 through 7. Dijkstra's shortest path algorithm, if you recall, constructs these shortest paths in increasing order of length. Okay. So you start with the shortest path from vertex 1 to itself, its length is 0. Then you get the next shortest path, next meaning the one of the next smallest length. Okay. And then you go from having 2 shortest paths to 3 to 4 till eventually you have 7 shortest paths. The way you get the next shortest path is you look at one edge extensions of the shortest paths you already have. Okay, so you start with the path from 1 to 1, and then from there we look at all the one edge extensions. So the path from 1 to 1, you can extend it. You can go to vertex 3, you can go to vertex 2, you can go to vertex 4, and you can go to vertex 7 through a one edge extension. And of all the possible one edge extensions, you take the smallest one. Okay. So this would have a total cost of 2, total cost of 16, total cost of 6, total cost of 14. The shortest is 1, 3, total cost of 2. So your next shortest path in your sequence is 1, 3. Okay. So now I've got two shortest paths. Then I'll look at one edge extensions of both of these shortest paths, and from all of those possibilities, pick the shortest. That'll give me 3 shortest paths. And you repeat this process till you end up with 7 shortest paths, or until you can't add another shortest path. Okay. Right, so that's basically how Dijkstra's algorithm works. And in terms of implementation, what you do is you keep track of a quantity called d, length of the shortest one edge extension that gets you to vertex I. Okay. And then in each round, you have to find the smallest d, okay, the smallest as yet unselected destination. You add that to your collection of shortest paths, and then you update some of the d values by using edges leaving this new vertex. Okay. All right, so hopefully that sounds kind of familiar. Okay. I don't expect you to understand Dijkstra's algorithm for what I said here, but I expect you to remember Dijkstra's algorithm based on what I said here. Okay. All right, so the things you do on this quantity d, okay, on each iteration where you add the next shortest path, you take this collection of items d, and from there you remove the destination with the smallest value, okay, a destination to which you don't already have a path. Okay. So you do this really n minus 1 times if you have n vertices. Okay. So you're doing it order of n times. So you got order of n remove min operations on this set of d values. When you select a vertex, the next shortest path, you decrease some of the d values, because now you have a shortest path for whom you look at the one edge extensions, and that decreases some of the old d values. Okay. This is done a total number of times, which is equal to the number of edges in the graph. Okay. All right, and these are the two operations you really perform on this collection of values. The typical way to implement Dijkstra's algorithm, at least the way that's taught in undergraduate courses, is to employ an array for d. Okay. So to do the remove min, you just check all of the n values of d, forget the ones for which you already have a destination taken care of, and from the remainder pick the one that has the smallest. Okay. And that takes you order of n time to do the remove min. Okay. And to do the decrease key, you look at an edge, you make a random access to the appropriate d and reduce its d value. Okay. So the decreases you do n remove mins, each taking n time, that's n square. You do e decreases, each decrease taking 1 time, that's e. And since the number of edges cannot be more than n square, your overall complexity is n square for Dijkstra's algorithm using an array. And that's typically what you would have seen in an undergraduate data structures class. Okay. Now you could use a min heap. Okay. If you use a min heap, then you got n remove mins, which would take n log n time. Okay. And you got e decrease keys, so that's e change key values. Each change key value would take log n. So it'll work out to n log n plus e log n. Okay. If the number of edges is small, so if you have a sparse graph, e being of the order of n, then this works out to n log n, and you're doing better than the array. But if the graph has is dense, it's got of the order of n square edges, it works out to n square log n, so that's worse than the array. Okay. So depending upon whether you have a sparse graph or a dense graph, a min heap may give you better or worse performance. If you use a Fibonacci heap, okay, then the remove min operations, okay, so we're going to have a sequence of remove mins. That sequence will have about n remove mins in it. We'll have a sequence of decrease keys, and there'll be e decrease keys in the sequence. While an individual remove min might take order of n time, or a specific decrease key might take order of n time, we really care about the total running time of the algorithm. So I'll use the amortized complexity to figure out the cost of the whole sequence of n remove mins and e decrease key operations. The amortized complexity here is log n, and over here it's 1. So the entire sequence would take n log n plus e amount of time. Okay. So if you implement Dijkstra's algorithm using the Fibonacci heap, your algorithm would run in n log n plus e time. Now this is not amortized time, this is actual worst case time of your algorithm is going to be n log n plus e. Okay. So if you have a dense graph, then e is of the order of n square. This works out to n square. You're doing the same as an array. If you have a sparse graph, e is of the order of n. This is n log n. You're doing what the heap was doing. So you're kind of getting the best of both worlds. Okay. So regardless of the kind of graph you're dealing with, the Fibonacci heap would give you good performance. Okay. All right, any questions about that? Okay. All right, let's take a look at another one. This is Prim's minimum cost spanning tree algorithm. Again, something you should have seen in an undergraduate data structures class. And the same is there. You can implement this algorithm using an array, and the complexity will turn out to be n square. Again, it's a greedy algorithm. It's the same kind of thing. On each round, you select the next vertex to include using a greedy strategy. So you do a remove min. Based on that, you have to change some of the values. Okay. So complexity is the same with the three different choices of data structures. The Fibonacci heap gives you the best performance over a wide range of densities for the graph. All right, so with that as motivation, let's take a look at the Fibonacci heap itself. Again, there's a min Fibonacci heap and a max Fibonacci heap. The symmetric structures, we look at the min version. Like a binomial tree, it's a collection of min trees, except this time the trees may not be binomial. All right, the node structure we're going to employ here, each node will have a degree field, a child field, and a data field. That's kind of the same as in a binomial heap. We're going to have not just a sibling field, but left and right siblings, because we're going to maintain doubly linked lists here instead of singly linked lists. Okay. So the siblings will be linked together in a doubly linked circular list rather than a singly linked circular list. Each node will have a parent field. Okay. Each node will have a field called child cut, which will be true or false, and child cut will be true if a node has lost a child since the most recent time it became a child of its parent. Sounds a little complicated. It'll become clear when we look at an example. Okay. Right, so that's a Boolean field. That's a pointer field and two pointer fields. Okay. Right, we'll see in a moment why we need to have doubly linked circular lists rather than singly linked circular lists. Okay. Let's look at an example. Right. So you have a collection of min trees. Okay, so here I've got this pink one here, a yellow one, 2, this one here, 3, 4, 5, 6 min trees. Okay. Right, so there are 6 min trees in my Fibonacci heap. In this particular case, all of them are binomial trees, but they don't have to be. Okay. You could have other kinds of trees. Again, the kinds of trees that can arise are dependent on how we define the algorithms. Just like in a binomial heap, we ended up with the binomial trees by virtue of how we defined the algorithms. Okay. Now, to see why we need, I guess I should point out, some of the fields are not shown here. Parents not shown, and child cuts not shown. Okay. Okay. All right. Suppose you want to perform some of the new operations, like a arbitrary remove. Okay. So people have pointers external to the structure in order to do things like arbitrary remove and decrease key. Okay. And what that means is, if somebody came to you and said remove the 4, okay, and the way you implemented that was by using the idea of copying the forward item in a singly linked circular list. So we copy this tree over here. So basically you copy the content of this node into that node, and then delete this node. Okay. So it works as far as removing the 4 is concerned, but the problem you have is that external to you there are people keeping track of the fact that the 5 was sitting here. Okay. And you took the 5 out of there, and the next time around the user doesn't know, you don't know where these pointers are that are coming to the 5. So the next time around somebody's probably going to come and say change the key in this node to 2, but you went and deleted that node. Okay. So so to get things to work here, okay, so to get things to so to get things to work right, because you're supporting an arbitrary remove and a decrease key, both of which require the user to keep track of different nodes, you can't actually start moving things from one node to another. Okay. So if somebody says remove 4, you must physically remove that node and not one of the other nodes. Okay. Okay. All right, so that's why we need doubly linked lists here. Okay. So with a doubly linked list, you can remove this fellow from its doubly linked list in order one time by just changing its left and right sibling pointers. Okay. All right, so let's take a look at how the operations work. The first 3, insert, remove, min, and meld, work the same way here as they worked for binomial heaps. To insert an item, you create a min tree, put it into your collection of doubly linked min trees. To meld, you combine 2 doubly linked circular lists into one. To do a remove min, you remove the item, take its subtrees, take the remaining trees at the top level, do pairwise combines, leaving behind no 2 trees with the same degree. Okay, so all of that is the same. All right, suppose you now want to do an arbitrary remove. Okay, so to do an arbitrary remove, the user has to point to the node that contains the item that's to be removed. Okay, let me back up a bit. When I talked about the insert, when you do an insert, you put an item into a node, and then the insert can return to the user the node in which you put the item. That's how the user keeps track of which node contains the item that he may later want to do a decrease key on or remove. Okay. So the insert gets modified slightly. It returns a pointer to the node in which the item was placed. Okay. All right. So later the user may decide to remove the item in a node, so he invokes this method, gives you a pointer to the node which contains the relevant item. Okay. You check to see if the user is actually trying to use this as a sneaky way to do a remove min. Okay. So if the node happens to be pointing to the minimum item, you just invoke the okay. So if it happens to point to the minimum item, you invoke the remove min method. Okay. All right, so this is not an escape from removement. Okay. All right, so let's assume that the node doesn't point to the minimum item in the Fibonacci heap. Okay. Let's say it points to some item here. It doesn't have to point to one that has a parent. It could, for example, be pointing to the 6 or the 5. That's okay too. It just shouldn't point to 1 at this time. Okay. All right, the things we need to do are we need to take this subtree out of its doubly linked circular list of siblings. Okay. So you can do that in order one time. Take a node out of a doubly linked list. Well, once you take it out, okay, like I've done now, you then need to take this doubly linked list of subtrees, okay, and meld it into the top level doubly linked list. Okay. So you have two doubly linked circular lists. There's a top level one which has 1, 6, 5, and now there's one which has this 10 and 5. Okay. So I'm going to take these two doubly linked lists of min trees and combine them into a single one. I'll end up with a top level doubly linked list that has 5 min trees in it. All right, so this combining takes order one time. I have to change the parent fields in these nodes. These were previously pointing to the 4. So the parent fields have to be changed to null to indicate these are now top level nodes, they're roots. Okay. So the time required to change those parent fields will depend upon the degree of the 4. How many subtrees did it have? And when you do the analysis, we'll see that the number of subtrees is still log n. Though the base is different, it's not log of n base 2, it's really log of n base phi, where phi is the so-called golden ratio, 1 plus root 5 over 2. Okay. So it's still logarithmic in n, though the base is different. Okay. So there's a logarithmic number of subtrees whose roots have to have their parent pointer changed to null. All right, so the actual complexity of this operation, if this is all we did, depends on how many subtrees that 4 had. Okay. And as we'll see later, that could become as much as log n. Okay. But we're going to be adding some more extraneous work in order to get that log n degree. And that extra work is going to take order of n time. Okay. All right, but for now, you've got order 1 to pull it out, order 1 to combine the two lists, some amount of time to change the parent fields to null. The min heap pointer doesn't change because the min element stays what it was. We did not remove the min element. There is no pairwise combining of equal degree trees. Okay. Now this isn't all that there is to it. There's going to be something else that we'll talk about in a little bit. And once we do that, the actual complexity will go up to order n. All right. All right. Any questions about removing an arbitrary element? Well, by element, I mean, well, first, a single-ended priority queue is a collection of elements, and each element has a priority associated with it. So in this case here, this min tree represents 2 elements. One has priority 5, one has priority 6. There may be other attributes associated with an element which are not shown in the pictures. So if I say remove the node here, that means take out the element that is stored here, and its priority is being shown here 5, but it's got other fields. You just take out whatever's stored in the data field of the node and throw it out. Okay. All right, other questions? Well, let's look at how we plan to do a decrease key. Again, here, the user has to tell you which node contains the item whose key you want to reduce, and then he has to tell you by how much the key is to be reduced. Okay. And that's supposed to be a non-negative amount. Okay. So you're going to decrease it. So it's not a sneaky way to actually increase the key. All right, so let's suppose we are to decrease the key of the element stored in that node. Currently, the key is 4. Okay. Once you decrease the key, okay, when you decrease the key, you don't affect the min heap relationships with respect to the descendants. Okay, this becomes smaller, so this whole subtree is still a min tree. The only problem that decreasing this key can create is a problem with respect to its parent. And of course, it may have a grandparent and great-grandparent and so on. Okay. So if I decrease the key from 4 to 3, I don't have to do anything. I just leave things the way they are. If I decrease the key from 4 to 0, I have a problem because now my parent has a bigger key than I have, and that's not permitted. All right, so we decrease the key. If the key drops below that in the parent, we're going to take the tree out. Fortunately, I have a parent field, so I can easily check whether my key drops below that in the parent. If it does, I pull it out. We've seen how to pull a tree out from a doubly linked list. That takes order 1 time. Okay. And then we'll take that tree and put it into the top level doubly linked list. Okay. So very similar to what we were doing in the case of an arbitrary remove. An important difference, which is what makes the amortized complexity of this operation different from that of an arbitrary remove, is that when you put things back, there is only one tree that goes back. In the case of an arbitrary remove, the root disappears and all of its subtrees come in. And the number of subtrees can be logarithmic. Here there's only one. Okay. And that's the important difference between these two operations. And that's why this one is going to have an amortized complexity of 1, and the other one has an amortized complexity of log n. Okay. All right, so I decrease the key, I pull the tree out, put it in to the top level. Okay. Then I have to check this key against the min value, because I might have dropped below the min value. I update the min pointer. And in this case, I'm actually dropped below the old min value, so the min pointer is now going to come over here. Again, there is no pairwise combining of trees that have the same degree. Okay. All right, so the actual complexity here so far is order 1. Whereas in the previous case, we saw that it was really order of the degree of a node. All right, questions about how a decrease key is done? Right, when you do the operations in this manner, the height of the trees that are created can actually become fairly large. You can get trees whose height is order of n. Right, the important thing is that the degree of these trees will be low. We're not going to be able to prove that today, but if you watch the lecture that's posted on the web, which has the analysis, it's shown out there that the degree is logarithmic. Right, to complete the two operations, we need to do additional work. If we don't do the additional work, the amortized complexity is not as stated in that table. Okay. So to get the amortized complexity, to get the degree of the trees to be logarithmic in the number of nodes they contain, we need to perform additional work. Okay. And that additional work is in the form of something called a cascading cut. Okay. The two operations, arbitrary remove and decrease key, they cut a node off from its parent. Okay, you take it out of its doubly linked circular list of siblings, effectively you're cutting it off from its parent. Okay. Now, if you permit too many nodes to get cut off from their parent, then you get provably bad performance from the amortized point of view. You have to control the number of children a node can lose in this process. Okay. And that's where this child cut field comes in. The child cut field keeps track of how many children a node has lost. And in fact, in the pure form of Fibonacci heaps, a node is allowed to lose only one child. And to keep track of that, you only need a Boolean variable true, false. True if you've lost a child, false if you haven't. Okay. So if you've lost a child in the past, then if you lose one more, you are cut off from your parent as well. So in a cascading cut, when a node loses a second child, it is cut off from its parent, and then this thing could trigger the same operation at its old parent, because now the old parent may have lost a second child, in which case it gets cut off from its parent, and so on. And this continues until you reach a node that is losing its first child, or until you reach the root, in which case everybody has been cut off. Okay. Let's see an example that will make it pretty clear what happens in a cascading cut. All right, so I'm asked to say either remove this element 8, or I'm asked to decrease the key of 8, and it happens to drop to below 7. Okay. So whatever you're doing, you have to cut this subtree out. Okay. Right, in this case, I'm decreasing it by 2, it drops to 6, I cut it out. Okay. So when I cut it out, okay, I examine its old parent. Its old parent had a child cut field of true, which meant it had lost a child previously. Okay. So now it is losing a second child, and that's not permitted. Okay. Or I shouldn't say it's not permitted, but when that happens, you cut the parent off from its parent. Okay. So the 7 is going to get cut off here. Okay. So we cut the 7 out, okay, and it moves up to become a top level tree. Again, keep in mind that even though in this figure this node is simply a single node, okay, but in reality it could have a large number of subtrees, and all of those get moved along with the 7 up to the top level. Okay. So a large number of subtrees get promoted up to the top level. Right, now the 7 was cut off from its parent, but its parent already had a child cut field of true, meaning that it had lost one child in the past. Okay. So that means you're going to cut the 4 off from its parent. Okay. And when you cut the 4 off, its subtrees go along with it, so it moves up to the top level. Yes?
Once a tree is cut off and moved to the top level, the child cut is such false?
When it moves up, it becomes a root, and for a root node, the child cut value is not important because we never use it for a root. Okay, so you could set it to false. It doesn't do you any good to do that, though. All right, so at this time, the 2 lost a child. It lost its child 4. This is the first time it's losing it. Its child cut value is currently false, so we change its child cut value to true. Okay. We don't cut it off from its parent. We just leave it here as true.
Why do we leave it?
Pardon?
The value of that 2 is true, set to 2.
Yeah.
Why don't you cut it off?
Oh, what? All right. Question is, well, why don't we just cut it off in any case? Why wait for the second child to go? Okay. Again, this has to do with the proof of the amortized complexity. Okay. If you cut off the fellow that is false, the proof will not go through. Okay. Because now the way you pay for this child cut. Okay. Now, a little while ago I said the height of these things can be order of n. Okay. So the child cut operation has an actual complexity of this order of n because you start somewhere deep and you keep going up, and if everybody had true on it, you end up at the root. That costs you order n. Okay. But you got to pay for this somehow in the amortized scheme to bring the complexity of the other operations down to log n and 1. And the only way to do that is if all of the child cut cost is borne by somebody else and not by the decrease key operation or by the remove, the arbitrary remove. So somebody else has to pay for it. Okay. And the way you end up paying for it is that the operation that did the first cut, okay, leaves a credit of 1 on the true. So everybody who does a cut ends up paying 1. So it increases their cost by 1 instead of by a huge amount. Okay. And so if you went off and cut somebody with a false, there's no credit sitting on the false to pay for that cut. Okay. So again, if you watch the lecture on the analysis, you'll see that we can arrange for every node with a child cut value of true to have a credit of 1 sitting on it to pay for the time it gets cut off from its parent. Whereas the falses don't have any credits on them, and so if you do any work out there, you're in trouble. Okay. All right, so getting back here, so the 2 had a subtree whose root was 4. We cut it off and moved it up. Previously, its child cut value was false. I change it to true, and I don't go any further up the tree. All right, so that's how the cascading cut works. Or any questions about how a cascading cut works? Yeah.
So why is it that you remove the node when the child cut value is set to true?
Why do I do a cut
Yeah.
when the parent's child cut?
So why do you actually move the 7 up the top level?
Right. Why did I do that? Well, let's go back. Okay. All right. So I decreased the key here by 2, and then I had to take that fellow out. Okay. And before I did that, it had the child cut value of true. Okay. So at this time, this fellow has lost a second child. And the question is, well, so what? Why don't we just leave it? Okay. Again, it has to go back to the proof. Okay. If you look at the proof carefully, you'll see that you can extend the proof so long as these fellows lose only a constant number of children. Okay. So I could change it, instead of keeping a Boolean value here, I could keep a counter 0, 1, 2. If it has become 2, well, then I cut it off, or if it becomes 3. But if you allow it to lose an arbitrary number of children, then the amortized complexity is no longer order 1 for the decreased key or logarithmic for the arbitrary remove. Okay, so it's all got to do with being able to prove a desired amortized complexity. Okay, all right. The other questions with the child cut or the cascading cut operation. Okay. All right. So the question that probably remains is, the cut operations that you do when you have an arbitrary remove and decrease key, they change child cut values from false to true. Okay. So the question then would be, well, when do these things become false again? Because if you do these operations long enough, everybody becomes true or becomes a root. Okay. When you do a remove min operation, that's the only operation in this whole collection of operations that makes one node a child of another. Okay. So the remove min operation, when it makes one node a child of another, it sets the child cut value of the child to be true, to be false. Okay. So that's why we had this somewhat complicated definition of child cut up front, which said that you count based on the most recent time you became a child of your parent. Okay. So you can lose nodes, like this fellow here can lose a subtree, his child cut can become true, but then if you do a remove min and it becomes a subtree of somebody, his child cut becomes false again, and now it can lose another subtree, and that's okay. Okay. So it's not that you can lose a child only once in the history of the system. You can lose children many, many times, but only once for each time you become a child of your current parent. Okay. So the remove min operation resets the child cut field of one node. Okay. Every time you do a pairwise combine, okay, there's one node whose child cut field gets set to false. That's the fellow who becomes a subtree of the smaller tree. Okay. All right, questions? Okay. All right, so as I said, we will not be doing the analysis in class, but there is a pre-recorded lecture that does do the analysis, and you can get that by following the link. It's under instructional material. Go to the bottom of that page. There are links to some lectures from the past. Okay. All right, so we'll stop